right, hello everyone. Strange times we're in. I'm hoping that we can continue the rest of the semester with some measure of continuity in material. I know the circumstances you find yourselves in are incredibly varied. Some of you are probably going to have pretty much uninterrupted life, and you'll have access to a lot of the same resources, materials you had beforehand, and some of you may have profound disruptions. Maybe you're ill yourself, you're taking care of ill family members, you're having issues at your job, and those are certainly higher priority than continuing work in our class and devoting as much effort to our class as you can. So I understand that your circumstances are all going to be different, and I expect that accordingly your performance in this class and the amount of time you're able to commit to this class is going to vary considerably based on your life circumstances right now. So I just want you to know that I appreciate you all. I understand that you'll all be in very different places, and my goal in the next several weeks as we go through this together is just to make sure you have whatever resources you have to be as successful as possible. If there's anything I can do at any time, whether it's related to our class or not, to support you, please don't hesitate to reach out and contact me. I'm happy to help you in whatever way I can, and I'm here for you. That said, I'm going to try to record a number of short videos, just kind of like the beginnings of our class, where we start off typically by having a discussion of a particular reading, and then we go into some in-class exercises together. Obviously, those are going to be hard to replicate, but what I hope is that I'll get a chance to meet with all of you, maybe in small groups or individually, at various times as you need to talk about these ideas. But as I said, these short videos are really just meant to give you a little bit of the background, just to unpack some of the readings that we share together in class, just like we've done in class. Unfortunately, not in as dialogic a format. So I'll be standing here talking, and you will have a chance to ask me questions by email if you would like to. If you want to send me a short video of your own, that's fine. Whatever way you need to get in touch with me to ask questions. But let's go ahead and get started. I'll pick up where we left off. We finished chapter 4 before spring break. So we're going to pick up at chapter 5. Chapter 5 starts to talk about the method of mathematical induction, which is a really powerful proof technique, which has to do with proving a statement is true about a series, or a sequence rather, of cases, usually having to do with the natural numbers, like the first, the second, the third, and the fourth, and so forth. So proving a statement is true about a variety of elements in some sort of sequence. So to start with, we're going to talk about what a sequence is. So a sequence is, formally, it's a function whose domain is a consecutive set of integers. So for instance, you could have a function defined from the integers 4 through 7, and you would have the 4th, 5th, 6th, 7th term in a particular sequence, and you specify a value for each of those terms in the sequence. So when I talk about a sequence, we often denote it by giving a name to the terms of the sequence, a sub n, for instance. And we might specify the range for the sequence. So we might say from 1 to infinity, for instance. And all this is a list of elements in order. So it's kind of like a set in the sense that it's got a bunch of elements in it, but it's not like a set in that order matters. Here, the order is very important, and we could repeat. That's another way in which it's different from a set. So it could be the case that A1 and A2 are the same, or A1, A2, and A3 are the same, and so forth. So there's a lot of divergence from a set in that regard. When we talk about the terms of the sequence, we're talking about the values A1, A2, A3, etc., and the index is the position of a term. So for instance, we would talk about the number A3 as the third term in this particular sequence, but the index of that term would be the number 3. So A3 is the term, and 3 is its index. In the case of a finite sequence, because this is all we're saying formally is that this is a function whose domain is some set of consecutive integers, it could be that it's a finite sequence, so it starts at some fixed point and it ends at some other fixed point. We can talk about the initial and the final term of the sequence, which would be the first and last terms that appear. In the case of an infinite sequence, however, you don't have perhaps an initial or a terminal, an initial or a final term. So it could be that it goes off infinitely far to the left, back to negative infinity, or it goes infinitely far to the right, to positive infinity, or both. In which case we would say, in either of those cases, we'd say we had an infinite sequence. If it's not infinite, of course, it's finite. Usually we're going to be interested in sequences that have a particular formula that is given to us, an explicit formula for finding the terms of a sequence. So for example, let's say I suppose that a sub n is given by some function, let's say 2 to the n, and we want to specify the indices for our sequence. So we'll say it's for all non-negative integers starting at 0. So then, if we want to give an explicit formula for our sequence, we're starting at 0 and going to infinity. And so we would have our a0th term would be 2 to the 0. Our a1 term would be 2 to the 1, 2 squared, 2 cubed, and so forth. Because we never stop, because we've said this is an infinite sequence, we would just put ... like we would for a set when we're giving enough terms to indicate a pattern. And then we can simplify this a little bit. Obviously, 2 to 0 is 1, 2 to the 1 is 2, 2 squared, and so forth. So we can often go from an explicit formula for a sequence to just a list of its terms. On the other hand, we might be able to go the other way. So for example, if I were to list the terms of a sequence, the first few terms of a sequence, -1, 4, -9, 16, and so forth, we can look at this and see that there are two patterns sort of interacting here. One is that we have alternating negative sign, so every other term has a negative sign in front of it, and also the terms are going up as the squares go up. So it looks like there's probably some pattern that involves -1 to some power, and there's also some pattern that involves the square of the index of the term. Because each time we step the index up by 1, we go to the next square. So putting those together, we can see again a common trick for making a negative sign pop into every other term is to say -1 to the index. Because here, for instance, when n is equal to 1, the first term will have -1 to the 1, which is negative. For the second term, we would have -1 squared, which is just +1, so the minus sign goes away, but it comes back for the third term, -1 cubed, which will give us -1 again. So there's that component, but then we want to incorporate the fact that each term is going up by a square. So we can throw in an n squared. And of course, combining those, well, there's really nowhere to combine those, never mind. That's probably the best formula we're going to come up with for this one. So we went on the one hand from having an explicit formula to coming up with the terms of a sequence. On the other hand, we were able to take the terms of a sequence and figure out what an explicit formula for it would be. All right. I'm going to go ahead and erase, which gives you all a chance to take a coffee break, take a bathroom break. catch up in your notes. Rub your dog's belly. Apparently dogs are immune to coronavirus, which means that you should probably suspect that the dogs are at the heart of all this because they're immune and they have arranged so that you have to stay home all the time to be with them. So it sounds like the dogs may be responsible for this. All right, let's just look at another example of finding the first few terms given an explicit formula. So if I say C sub n equals 3 minus 2n, and I ask you to find, if I ask you to find the first 5 terms, or actually, yeah, first 5 terms starting at 0, then all you have to do to find those terms is to take those 5 values and plug them into this formula. So you would get 3 minus 2 times 0, 3 minus 2 times 1, and so forth, up to your last term. And then plugging in that formula, we get 3, we get 1, and each time we're taking 2 more away, so we're getting minus 1, minus 3, and then finally this last term is going to be minus 5. 3 minus 8 is minus 5. So this is a pretty straightforward process. I'm going to do one more of these examples, and then I'll ask you to find the rest of them, just to test yourself. So let's put it this way. If I give you a list of the first several terms in this sequence, b sub n, let's say it starts with 1/2 and goes to minus 1/6, 1/12, minus 1/20, and so forth. We can see there's kind of the pattern we had before, only now the first term, we have that alternating minus sign again, only now the first term doesn't have a minus sign. So if we want this one to be b sub 1, b sub 2, b sub 3, b sub 4, and so forth, we want to make sure that we add a plus 1 to our power here. You see why that is? Because now, for b sub 1, 1 plus 1 is 2, so minus 1 squared is the term that gives us our, or rather make sure we don't have a minus sign there. And now when n equals 2, we have 2 plus 1 is 3, minus 1 cubed is minus 1, so we do get a minus sign, and so forth. And then the other pattern that's going on here, you can probably see, is that we've got 2 times 1, we've got 2 times 3, we've got 2 times 6, we've got 2 times, oh no, I don't know what the heck I'm talking about. It looks like this is rather 1 times 2, 2 times 3, 3 times 4, 4 times 5, and so forth. So it looks like there's some pattern involving the product of 2 consecutive integers. Starting, in this case, it looks like starting with n, and then n plus 1, also multiplied in there. So again, when n equals 1, we have 2, which is really 1 times 2. When n equals 2, we have 6, which is really 2 times 3. When n equals 3, we have 3 times 4. When n equals 4, and so forth. And so this gives rise to a pretty simple formula for b sub n. And just for practice, I'm going to ask you to do a couple more on your own. And if you would like to send me any questions about these, feel free to shoot me an email. take a little time to see if you can figure out the pattern giving rise to an explicit formula for this sequence and for this one here. And I'll give you a hint on this second one. It might behoove you to remember your trick. So 0 square root of 2 over 2, 1 square root of 2 over 2, 0, and so forth. Looks like it begins, to some extent, begins to repeat, but I'll let you think about the unit circle to get a hold of that one. All right. We're going to switch to, in just a moment here, we're going to switch to a couple of special kinds of sequences involving sums and products. And then we'll talk a little bit about factorials and binomial coefficients, because those show up in a lot of different sequences. Let me go ahead and erase real quick again. I'm going to try to keep these videos pretty short, no more than half an hour. So if you see me staring at the screen, it's mostly me just checking the time. I realize you probably have a lot of important things to attend to these days. Let's see. All right. So like I mentioned, a couple of specific kinds of formulas that show up in sequences quite frequently are sums, and you may have, if you've taken calculus, you've seen sigma notation before. And the notation we're going to use for sums is similar. So often you'll have a sequence of sums. This notation, the sigma notation, is just another way of indicating, a shorthand for a sum starting at some indexed value and ending at some other indexed value. So for instance, if I write the sum from k equals m to n of a sub k, and by the way, the LaTeX for this notation is \sum, and then you can do subscripts and superscripts as needed to get that. But if I write that, what that means is I'm starting my summation at a sub m, I'm adding to it the next term, and the next term after that, and so forth, and stopping at this upper limit of the summation right there. Products can be written similarly, and are probably a little less common. But when I use similar notation using a capital pi symbol instead of a capital sigma, by the way, the LaTeX for this is \prod, P-R-O-D for product. This refers to, much like with the sum, now you're just taking the product of successive terms. So for example, if I wrote the sum n equals 1 to 5 of, let's just say n. This is perhaps one of the simplest sequences where you're just taking the number itself. This would be 1 plus 2 plus 3 plus 4 plus 5, which turns out to be 15. Another example, examples. What if I took the product n equals 1 to 4 of 1 over n squared? That would be taking 1 over 1 squared times 1 over 2 squared times 1 over 3 squared times 1 over 4 squared, which is 1 over some very big number. You can figure out what that would be. It's very hard to crack jokes without an audience on hand to laugh at them. All right. Now there's some basic properties that I'm not going to go over regarding sums and products that are pretty simple. For instance, you have an associativity and commutativity of sums, which allows you, if you have a finite sum, to rearrange terms. So for instance, if you had a sum of a bunch of A terms and then a sum of a bunch of B terms, you can rearrange things so that the A's are added intermittently with the B's instead of adding all the A's first and then adding all the B's to that. There's also a distributivity. If you had some constant outside multiplied by a sum, you can take that constant and multiply it through, and you would have the you'd have distributivity of multiplication over addition as you normally would. You also have products of products. So if you had a product of a bunch of A terms multiplied by a product of a bunch of B terms, you could multiply those together in any intermittent order that you wanted to. And so your book will have a few formulas, a few rules for working with such formulas to simplify things. Another thing to note is that in this sort of a formula, this variable right here, if you've had calculus, you might remember from an integral formula, that's really called it's a dummy variable. It's like a placeholder that if you notice over here, it goes away. There's really, in the ultimate object that you're interested in, the sum itself, the index, the placeholder here, doesn't appear at all. It's just a placeholder in the notation. So we could make that pretty much anything we wanted to. We could say the sum for smiley face equals m to n, a sub smiley face. And it would be the same thing. We could say frowny cloud equals m to n, a sub frowny cloud. It doesn't matter what notation we use for that variable because it's not really a part of the final formula. All right. There are just a couple of other formulas I want to mention again because they show up quite frequently when dealing with sequences. Then we'll do a few more examples, and we'll call it a wrap. I'm going to try to not over-edit these videos, so my apologies if they're kind of rough, because just as you all have a lot going on in your lives, and I hope that you attend to things as they are higher priority, I've got a lot going on too, and I appreciate your understanding that I'm not going to take a lot of time to edit these and make them really polished. Okay, the other two ideas I wanted to mention were factorials, which we've already encountered before, but just as a reminder, the number n factorial, and this is usually if n is some integer greater than 0. The number n factorial is given by n times n minus 1 times n minus 2, and so forth down to 1. It's the product of all the integers beginning with n and ending at 1. Now you might ask yourself, I allowed n to be equal to 0 here. It turns out, for formulaic reasons, 0 factorial is defined to be 1. That's just a really common designation. From this formula, so for example, we could fill out a little table if we wanted to of the first several values of n factorial, maybe down to 5. 0 factorial, as we mentioned, is 1. 1 factorial is just 1 again, because if you look at this, starting at 1 and going down to 1, you only have one term in the product. 2 factorial is 2 times 1, which is 2. 3 factorial is 6. 4 factorial is 24. And notice each factorial is really found by taking the previous one and multiplying by the new number that you're appending. So 5 factorial is really just 5 times 4 factorial, which is 120, and so forth. From this, we can develop Pascal's triangle and what are called binomial coefficients. So the so-called binomial coefficients are denoted in the following way. N choose R, that's the way we read this. And the reason we do is because the number I'm about to write down represents the number of ways, if you allow yourself to draw from a collection of n different objects, if you allow yourself to draw R of them out. So you've got a big box of n things, and you take R of them out. The number of ways that you could choose R objects from among those n, or n choose R, is the number I'm about to write down. So it's determined by taking n factorial, the number of objects you're choosing from, factorial, dividing that by R factorial times n minus R factorial. Now this looks like a pretty complicated formula, but it has a ton of patterns in it. It's actually related to many, many different sequences in math that come from a variety of locations. But the one that's most familiar to us is Pascal's triangle. So I'll write that down in a moment here, and then I'll describe one of the most important applications of this formula, in particular why it's called binomial coefficient. So I'll keep that formula up there while we look at a couple examples. So for example, let's find 3 choose R. And I should have mentioned, this is really, this formula really makes most sense when R is between 0 and n. So anytime we're talking about n choose R, it's usually going to be the case that R is between 0 and n. So if we want to, we could find 3 choose R for all R satisfying R being between 0 and 3, because that's the range that we're interested in if n equals 3. So just using our formula, we would have to find 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. 3 choose 0 using our formula would be 3 factorial divided by 0 factorial times 3 minus 0 factorial. And if you work out the details, notice, remembering that 0 factorial is 1, this is really just 3 factorial divided by 3 factorial. Now we could have expanded 3 factorial, but it's almost easier to see that they just cancel. Using our formula here, 3 factorial, 3 choose 1 is 3 factorial divided by 1 factorial times 2 factorial. Now here, there are a lot of different ways to get this, but since the numbers are small, we can really just work out what these are and get the formula 3. 6 divided by 1 times 2. We start to see an interesting pattern if we apply the formula in the next case, because we get 3 factorial divided by 2 factorial times 3 minus 2 factorial, which is just 1 factorial. And that looks like what we just got. In fact, there's a lot of symmetry in binomial coefficients. And finally, we'll see some more symmetry here. We apply the formula. In the case 3 choose 3, we get 3 factorial divided by 3 factorial times now 3 minus 3, or 0 factorial. So it looks an awful lot like the first one here. And in fact, that's not a coincidence. It turns out to be the case that there's a lot of symmetry as you go through. If you fix your value of n and you look going through all the different values of R, there's a lot of symmetry. And that's what gives rise to Pascal's triangle here. So you may have seen this handy way of really quickly developing all of the different binomial coefficients. If you start out by writing a 1 and then a 1, 1, and then for each successive row you start with 1 and add the 2 numbers diagonally above a given location. So between the 1 and the 1 from the previous row, I add them and I get 2. And then I end with a 1. The next row, 1, and then 1 plus 2 is 3. 2 plus 1 is 3, and then I end with a 1. We'll do a couple more rows. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and with a 1, and again, one more row maybe. Going through that same pattern, we get this triangle by adding, again, the two numbers diagonally above a given location. This is Pascal's triangle, and if you look, if you're looking for a particular n choose r, you look in the nth row in the rth location, or the rth element in that list. And of course, both of these start with 0. So starting with 0 in either case. That's not without. That's starting with 0. So for instance, if I told you to find 4, choose 3, you would look at the 0, 1, 2, 3, 4th row, and you would look at the 0, 1, 2, 3rd term. So this here would be 4, choose 3, for instance. So Pascal's triangle is really helpful because it gives us a quick way of generating binomial coefficients, because otherwise you'd have to deal with like 5 factorial, which is already 120. And what did I want to say about it? Yeah, it's just useful. One quick fact about binomial coefficients, why they're called this. So why binomial coefficients? Why do we call them that? Note that if we were to take a plus b, a binomial, and raise it to the nth power, a handy way to get all of the coefficients, coefficients, binomial, a handy way to get all of the coefficients for this expanded binomial power, I'll use the notation that we had before, is through this formula. So it's a summation formula like we were using before, where I'm intentionally using r as our dummy variable for the summation, because it corresponds with this notation here. That is, if you want to know the coefficient on the term a to the r, b to the n minus r, it's given exactly by n choose r. That is, these things that we're calling binomial coefficients can relate exactly to the coefficients of this expanded binomial power. All right, now I already broke my promise. I'm already a little bit over half an hour, so I'm going to wrap it up here and just and give you just a couple more questions for practice, and then go ahead and attempt to do the problems from section 5.1, and I'll send an email with due dates for those. I'll also post those on Moodle. We are switching to Moodle now, and I'll send you an email to that effect, because that's the easiest way to continue this at a distance. So just a couple of practice problems. If you could do these and let me know if you have any questions about them. So one way or another, find formulas for B0 through B7, where BK is 7 choose K. So kind of like I did above here, we found 3 choose R for various values of R. Now find 7 choose K for various values of K. And let's see if you can rewrite this. So here's another product, or another example involving products rather. Go ahead and rewrite this formula. The product from k equals 1 to n of 2k without the product symbol. So find a way to rewrite this value here, the product from k equals 1 to n of 2k. See if you can rewrite that without the product symbol. So there's a way of using some of the notation, some of the ideas we've gotten in this earlier on in this video to rewrite that without using a product symbol. So So thank you so much for your patience as we move to this new format. I know it's not ideal. I look forward to corresponding with you all. I look forward to continuing to read your homework and your emails. If you want to send me videos of your own, please feel free to do so. In fact, I will, in lieu of your presentation requirement, asking you all to present in class, I am going to ask you to produce just a quick video of you presenting a solution to one of the homework problems, whether it's starred or not. And I'll look forward to getting those. So thank you again for your time, your attention, and I'll be back at you soon with another video.